Hi everyone. I thought I would start out today's video with two little comics here. One's from xkcd.com, the first one on the left, and then the comic on the right is from Cyanide and Happiness, which is often terrible and vulgar, but this one's pretty funny and mathy. So give it a pause, give them a read if you want to, or just we'll get started on the section. In this video, we're going to look at section 4.9, which is applications to something called Markov chains. So we skipped 4.8. That one's not as entertaining, but this section is a pretty cool application. And we'll start out with referring back to something we looked at previously, was where we had a population in a city represented by a vector. And then we looked at how that population moved from the city to the suburbs and the suburbs to the city. And we previously gave that vector, that population vector, in terms of the actual total population, 600,000 and 400,000. Well, in this section, what we're going to do is convert that, look at that vector a little bit differently. And if you divide by the sum of 600,000, 400,000, or a million, divide each entry by a million, you get 0.6 and 0.4. Or we could write them as 0.60, 0.40, or 60% of the population is in the city, 40% in the suburbs. Okay, and we'll call that our x naught, our starting population, if you remember what we did before. And that vector, representing it that way, allows us to call it, well, a probability vector, right? We can interpret this as probability, and it's a vector with non-negative entries that add up to 1. Okay, so that's a probability vector. So that's the first shift in perspective that we take in this section. And then the other definition to start out the section is a stochastic matrix, and that's a matrix whose columns are all probability vectors. So it's a matrix consisting of these probability vectors. All right, and then we'll get to the big definition in the section, which I'm going to write down for you, and that is a Markov chain, M-A-R-K-O-V, chain. And what a Markov chain is it is a sequence of probability vectors, and they'll be called, nope, not a comma there, and they will be called x naught, x1, x2, etc. Then together with T-O-G-E, together with a stochastic matrix, and we'll call that capital P, a stochastic matrix P, such that, ST, the abbreviation for such that, x1 is equal to P times x naught, x2 is equal to P times x1, x3 is equal to P times x2. Hopefully you get the pattern there, or I could write that as a recursive definition. X subscript k plus 1 is equal to P times, oops, not subscript, is equal to P times xk for x equal to 0, 1, 2, etc. So the Markov chain here is that sequence of vectors. It refers to the x1, the x2, the x3, the etc. Okay, so here in our first example is that exact problem that we looked at back in section, it was 1.10, where we have 95% of the people that live in the city stay in the city, 5% move to the suburbs, 97% living in the suburbs stay, and 3%, and my arrow points the wrong way here in the picture, 3% move into the city. Then we've got our migration matrix over here on the right, and the 2014 population is 600,000, 400,000, like we were just talking about on the last slide. Then the initial distribution of the population in the region is given by x naught from before. So if x naught is the probability vector 0.6, 0.4, then x1 is equal to P, or actually in the case of this example, we are using an M times x naught. So we're basically doing what we did previously, but giving the context of probabilities or percents of the population instead of the actual number in the population. So that M times x naught is 0.95, 0.05, 0.03, 0.97 times 0.6, 0.4. Check that in your calculator. You get, let's see, 0.582, decimal 0.582, and decimal 0.418 for my x1 vector. In section 1.10, we got 582,418,000. Okay, so again, the context is just shifted a little bit. And then we could also find x2 is equal to m times x1, which is my same migration matrix, 0.97 times the previous vector, 582,418. And if you type that one into your calculator, you should get 0.565 and 0.435 for your x2. The distribution of the population, 56.5% live in the city, and 43.5% live in the suburbs. Our second example for this section is fairly wordy. I'm not going to read through all of it, but you can pause the video if you want to go and to delve into the details of what's on this slide. But our x vector, instead of the distribution of where people live in a city or in the suburbs, now we're looking at their voter registration. So we've got the first entry is voting Democrat, then voting Republican, voting Libertarian, and we can look at, from one year to the next, how that voting distribution changes. So in our P stochastic matrix here, right, what we're showing is that of the Democratic voters, 70% stayed Democratic, 20% switched parties to Republican, 10% switched parties to Libertarian. Of the Republican Party, 10% switched to Democrat, 80% stayed put, 10% switched to Libertarian, and then of the Libertarians, I'm not going to do that one out loud for you. You can kind of see that. So same type of problem, but instead of 2 by 2, we've got a 3 by 3 matrix here. It's a little bit bigger. The picture here, as I drag my slide up a little bit, we're basically looking at the same information, but in a slightly different visual way. I don't like this one as much. I very much prefer the stochastic matrix layout. But this is just showing the flow of how the distribution is changing. So then, if we're given an initial let me drag this up here. There we go. If we're given an initial x naught, an initial distribution within that population, where 55% are voting Democrat, 40% are voting Republican, 5% are voting Libertarian, we can use our stochastic matrix to predict or to determine what the distribution will look like in the next year, in the next year, in the next year. Now, in practicality, that P matrix is going to change over time, so this process would need to be looked at again in order to determine how accurately it's modeling the actual application. All right, but let's just follow through with this example. So if my x naught is this vector here, then x1 is equal to P times x naught, which is, and I'm not going to write down all the zeros, but 0.7, 0.2, 0.1, 0.10, 0.80, 0.10, 0.30, 0.30, 0.40. That gets multiplied by my x naught vector, 55, 0.40, 0.05. And again, if you type that into your calculator, you get 0.44, 0.445, and 0.115. So the Libertarian percentage of the population increased significantly, more than doubled. The Republican part of the population, they increased by 4.5%. And then the Democratic part of the population, they lost a lot, about 11%. Then we could do that just one more time, take x2, and that is P times x1, which I'm just going to write out the solution here. Democrats drop to 38.7%. Republican part of the population increases to 0.4785, and then the Libertarians still get a little bit bigger, 0.1345. So then the natural question is, what's going to happen as we keep moving forward into the future? Does that Democratic part of the population continue to decline? 55%, 44%, 38%? or so 36% the next year. How low does it get? And so what we can do is, because we have these calculators, we can just take and type in p to the somethingth power, because each time I multiply by a p, I get the next year's distribution. So p to the 10th power times x naught, p to the 15th power times x naught, and see what's happening. And I encourage you to pause the video and actually investigate that on your own. But we'll see with our next example what actually happens. Okay, so now let's do just that in this example. So we're going to predict the distant future, studying a Markov chain's long-term behavior. So here we have our stochastic matrix, and we can double check. 5 plus 3 plus 2 is 10. 2 plus 8 is 10. 3 plus 3 plus 4 is 10. So that is a probability, a stochastic matrix, because it consists of probability vectors. And here's my x naught vector. And then we're going to consider a system whose state is described by that Markov chain. The next step is p times the previous step. What happens as time passes? Compute the steady state vectors x1 through x15 to find out. Now, I'm not going to compute all of them by hand. I'm not going to write all of them down, but I'll do a few to give you an idea of what that looks like. So we start off with, well, let me write down x naught is 1, 0, 0. And those are both zeros. There we go. And then x1 is p times the previous step, p times x naught, which is 0.5, 0.3, 0.2, 2, 8, 0, 3, 3, 4. So this could be the distribution and what happens to the voter rolls in some other town. This problem doesn't really give us any context in that regard. But after the first year, what do we have? That 1, 0, 0 probability vector has changed 0.5, 0.3, 0.2 after the first year. And I'm not going to write out all the little steps in between now, but x2, p times x1, and if you compute p times x1, you get 374518, 0.37, 0.45, 0.18. So again, just taking a look at what we've done so far, the 1, 0, 0 has decreased to 0.5. 1 is decreased to 0.5, 0 has gone up to 0.3, 0 has gone up to 0.2, and then that 1 in the first entry, that's decreased further still, and the other two have increased further still. Let me write down a few more, and then I'll skip to later on in this process. x3, the entries in x3 are 0.329, 0.525, 0.146. So the 1 at the top entry has continued its steady decline. The middle entry makes good gains. The last entry still, what did the last entry do? No, that went back down a little bit. Let's skip to, say, x7. x7 we'll do next. We'll write that one down. And his entries are 3016, 0.5953, and the last entry is 0.1031. All right, so we can see the decline of the first entry has kind of slowed down a little bit, right? I've gone from 32, 33% down to 30% in the first entry. So, and then like 4 years later, so it's that decline has stopped. Let's go to x12 and see what we get there. x12 is 30005. 59985. Oops, another 0 in there. 0.59985. And then 0.10010. All right. So not a lot of change. And again, we've gone forward into the future by 5 years if this is a problem. And not any significant changes. It looks like, if we talk about limits and everything in calculus, right, it looks like our limit is approaching 30%. Our limit here is approaching maybe 60%. And here we're approaching 10%. And we don't need calculus to actually fully investigate this. And you'll see in a little bit how that works. But since the problem says out to x15, let's write that one down. x15 is equal to 0.30001. 59998 and 0.1123 zeros and then a 1. Okay, so our predictions probably are 30%, 60%, 10%, but what is the process by which I can find this with certainty? Well, let's just test one more thing. Let me drag this up a little bit. What I want to do is I want to take that our estimate, and we'll label it with a we're going to call it Q, and that's for a specific reason that you'll find out later. And let's say Q is 0.3, 0.6, 0.1. That's our kind of hypothesis here as to what we think that we're approaching. And I want to take and multiply P times Q. And I, again, would encourage you to pause the video and do this computation by hand. But if I multiply 0.5, 0.3, 0.2, and then it's 0.2, 0.8, just 0, and then 334, 0.3, 0.3, 0.4. If I take that matrix P times the Q, our conjecture, what we think it will be in the long term, if you do that multiplication out, take the first row times that column, and I have 0.5 times 0.3 is 0.15, 0.15 plus 0.2 times 0.3 is 0.06, plus 0.3 times 0.3 is 0.09. Add all them together, hey, guess what you get? 0.3. And then you take the second row times my column here, and 0.3 times 0.6 is 0.18. We'll be multicolored with this one. 0.8 times 0.6 is 0.48. 0.3 times 0.6, another 0.18. When you add them together, 0.6. Whoa. And then the last row times my column here. And what do we get? 0.2 times 0.3, maybe you already know, 0.06. 0 in the middle, 0.4 times 0.1, 0.04, add them up, 0.10, 0.1. Awesome. So P times Q equals Q. The next year, the population distribution doesn't change. The year after that, the distribution doesn't change. The year after that, the distribution doesn't change. You have approached your steady state. And that is the definition on the next slide. If P is a stochastic matrix, then a steady state vector, also known as an equilibrium vector for probability vector Q, is a probability vector Q such that P, Q equals Q. Boom. That's your steady state. When you multiply by P, you produce the same vector. And now that I can represent this concept with an equation, we can solve that equation for Q. I can solve this equation for Q, much like we did back with the consumption matrix, where we had the identity minus the consumption matrix times X equals the demand D, and then we augmented that. Well, we got the same thing going on here, because I can take that P Q equals Q, subtract my Q vector from both sides, and if I want to ultimately factor the Q out, I'm going to write PQ minus Q equals 0. I'm going to have an identity vector in front of Q, because then I can take and factor P minus I times Q equals 0. And that's how we're going to solve and find this equilibrium vector without having to go, times P times P times P and produce the whole Markov chain. I can get the steady state vector right off the bat. Now, example 4 is already done for us. They give us the steady state vector and then just kind of show, and you can check the computation and all that. They show that multiplying the migration matrix in example 1 by the steady state vector produces the same vector Q. So in that one, eventually, enough years into the future, 37.5% of the population stays in the city, 62.5% of the population stays in the suburbs. And even though some people move every year, the same number of people move out of each their respective locations. Now with example 5, we actually have to find that steady state vector for our given stochastic matrix up here at the top. There we go. So we're starting with that stochastic matrix, got to find our steady state vector. And so what I'm going to write in this one is px equals x. So we're not going to call it q just yet, because even once we solve this system, we have like a little bit more work to do before we can formally call it q, the steady state vector. But I am going to go through just like I did a minute ago. Px minus x equals 0. Put an I in front of my x vector so that I can factor x out and ultimately solve this homogeneous system. So we need first we need, before we can set up our matrix to get it into row echelon form, or reduced row echelon form, we need P minus I. And the P matrix, 0.6, 0.3, 0.4, 0.7, minus the identity, 1, 0, 0, 1, right? All that changes are the entries on the main diagonal. Those become negative because I'm subtracting I from them. So that gives me 0.3 here, 0.4 there. I'm going to get negative 0.4, and I'm going to get negative 0.3. And notice that it's just the opposite of what's below it. So that's kind of an interesting thing to like make a note of. So now what we do is we take negative 0.4, positive 0.3, 0.4, negative 0.3, augment that with a column of zeros because it's a homogeneous system, do a couple of row operations, and I mean just a couple. It should be done in 2 steps. What you get is, well, those 2 rows cancel each other out, right? They're exact opposites of each other. So I get negative 0.4, positive 0.3, 0, and then a row of zeros. And I can take one more step, so that's echelon form, but I can get this into reduced echelon form. Put my row of zeros at the bottom. My top row becomes, if I divide through by negative 0.4, you end up with 1, negative 3/4, and 0. So we can see that we have a free variable, and x1 is equal to 3/4 x2, with x2 being free. I can write down what a general solution looks like. It is x2 times 3/4 1, that vector. That's my general solution. All right, so how does that help us to find our Q probability vector? Well, what we can do is we can say, all right, I want to take a quote nice basis for our solution space, and I could use 3/4 and 1 as my basis vector, or I could use so we're going to choose a basis for the solution space. So we're going to say let x2 equal 4. Take a second, see if you can figure out why I used 4. Well, if I let x2 equal 4, then I'm going to say w, just label it with a w, is equal to 3, 4 as my vector. So that is one solution to this homogeneous system, as is 3/4 and 1, and that would have been fine. So that's the basis for my solution space. And then I want to convert that w, that solution vector, into a probability vector. So then the last step here is to convert w into a probability vector. And how do you do that? Well, I'm going to say Q is equal to 3/7 and 4/7. And if you're wondering first where I came up with 3/7 and 4/7, it's because that's their sum. 3/7, 3 plus 4 is equal to 7. So you divide by that sum, and that is a probability vector. 3/7 plus 4/7 is equal to 1. And then the claim here is that that is our steady state vector. And if you check, the original P matrix that we started out with was 0.6, 0.4, 0.3, 0.7. That was what we started out with. And we're going to take that P times Q. And if you do the multiplication, that times 3/7, 4/7. Check in your calculator, do it out by hand if you want to. You do also get 3/7, 4/7. So we have found the correct steady state vector. Cool. Now, you were probably wondering when we would get to a theorem in this section, because that's your favorite part of the course. And here we are. We get theorem number 18. Wow, that's a lot for this chapter. If P is an n by n matrix, regular stochastic matrix, and I'll define regular in just a moment at the bottom, what that actually means. But if P is an n by n regular stochastic matrix, then P has a unique steady state vector Q. Further, if x naught is any initial state, and xk plus 1 is P times xk for k equals 0 through whatever, then the Markov chain converges to Q as k approaches infinity. All right, so a couple things about this theorem. Okay, if P is this regular stochastic matrix, then it has a unique steady state vector. That Q is connected to the matrix P, not the initial state, not the initial condition. And that's kind of a cool thing. So it doesn't matter how the distribution looks at the beginning. Q is based on P. So in the case of the voting example, in the case of the population distribution example, it didn't matter what the starting point was. I would always approach that steady state Q. Kind of cool stuff. So what I skipped for a minute there was a definition for regular. So let me put that on there, because this stochastic matrix does have to be regular. All right, so we'll define that. And let's see. So what does it mean for a matrix to be regular? A stochastic matrix is regular if for some matrix power P to the K, if some matrix power P to the K contains I can write only strictly positive entries. So only strictly positive entries. So like our matrix in the earlier example that had a 0 in the bottom middle, that is not a strictly positive entry. However, P squared for that matrix was 0.37, 0.45, 0.18, 0.26, 0.70, 0.04, and 0.334522. So those are only strictly positive entries. So that would be considered a regular stochastic matrix, and we would be guaranteed to have that steady state vector Q exist. Now we've gotten to our last example in the section. We go back to the Republican, Democrat, Independent example from earlier, and we want to find the steady state vector for that example. And what we do is, if we solve P minus I times x equals 0, if we set up and solve that, I'm not going to go through all of the steps as I did because I just did that with the previous example, but we get 1, 0, negative 9 quarters 0, 0, 1, negative 15 quarters 0, 0, 0, 0, and 0 in the bottom row. So we get our free variable again, and we can write our solution in terms of that free variable. So x1 is 9 quarters x3, x2 is 15 quarters x3, and x3 is our free variable. If we choose a nice number, like let's say, 4, then x3 would equal 4, x2 would equal 5, x1 is 9. That solves the system. So the first solution solves the system. This solves the system, and we'll say that is our W vector. We just label it with a W, 9, 15, 4. And then from there, we can produce our Q steady state vector by dividing by 9 plus 15 is 24, plus 4 is 28. And if you do that, you get 0.32, 0.54, 0.14, and that's our steady state. So 32% of the population is going to be voting Democrat eventually, 54% is going to be voting Republican eventually, and 14% voting Independent eventually. That's the long-term solution. All right, that is the end of this section. Thank you for listening. Email questions. Let me know if you have questions. Ask questions. Thanks.